Hello viewers, welcome to my channel Connect Civilian. So this video second lecture for the eccentric footing design for rectangular column, okay, for uniaxial moment. So we have already done up to the reinforcement design, okay. So we have done for x and y for both the direction. Now we have to go for the check for one way and two way. So here for x direction how it is calculated. So we are going to uh, check for one way first. So our critical distance will be at a distance of small d from the face of your column. The small d will be your effective depth in x, and for the y direction, so first we are going to calculate for the x direction. So we have to also find the ultimate, sorry, the net upward pressure at the critical phase, that is at distance d from the face of your column, okay. So now by interpolation you can find. So how you have to use the interpolation we have already done in our first lecture. You can go and check from there. Same step you have to follow for the interpolation here also. So our net appropriation will be calculated at a critical phase here, okay. So our here at our net appropriation for extraction is coming as 147.98, okay. So same procedure will be followed as earlier. You can go and check from there. Now this distance will be our 1.909 and this will be 0.9591. This will be your effective depth in x direction. So your VU will be equal to upward pressure multiplied by area of our critical section. So what is upward pressure, how it is calculated? So here it is the average of both the pressures, that is 147.96 plus 182 divided by 2 multiply by 0.591 multiply by this. So this will be our critical section. So this area you have to also give. So it is 0.591 multiplied by 2 meter. So our VU will come as, so shear force will come as 195 kilonewton. So VU ultimate will be equal to 1.5 multiplied by 195. It will come as 293 kilonewton. So our nominal shear stress will be calculated as tau B is equal to VU upon B into D, and VU here it is calculated 293 multiplied by 1000 for the conversion in Newton per mm square, okay, but divided by B, that is the width of the footing, and here it is 2 meter, that is 2000 mm, multiplied by D, that is the effective depth in x direction, so it is 444. So our nominal shear stress will come as 0.329 Newton per mm square. And here one more thing, we have to consider the K value also. So here it is 1 as our total depth is greater than 300 mm. So here we have considered our total depth as 500 mm. So we have to take the value of K as 1. So it is mentioned in IS code 456 2000 on page number 72. You can go and check from there only. So our percentage still will be equal to the what area we have, what still we have given to in x direction. You have to add that, that is 2035 multiplied by 100 divided by 2000, that is the width of the footing multiplied by effective depth of the footing. So it will come as 0.229 percentage, and our tau c will come as design shear strength will come as 0.345. So how it is calculated? So it is taken from IS code 456 table number 19. So here we have also done the interpolation. So this will be your percentage of steel. So this is how we have taken the percentage steel, 100 into S upon B into D. So our percentage of steel will coming as 0.229. So it will come between 0.15 and 0.25. So we have to write the value 0.15, 0.229 and 0.25, and grade is M25. So for grade we have to write 0.29, we have to find the x value, and 0.36. So by same method, using the interpolation, you have to find the value, and our after interpolation our value come as 0.345. Okay, so how we have done the interpolation for the upward pressure, we have to follow the same procedure for this also by using the table number 19 from IS code 456. Okay, so if you don't know how to calculate this, I have already shown in my previous lecture for the in the slab design also, and for the square footing design you can go and check from there only, or you can also use the Excel sheet for the design. So here it is also mentioned the interpolation table, you can directly fill the value and take the value from there only. Now our design shear strength will be equal to 0.345 multiplied by your K value, that is 1. So it will come as 0.345 Newton per mm square, and this value is greater than our nominal shear strength, that is 0.329. So here it is also safe in one way. So similarly for the y direction, if you want to find, you can also find. So our Py will be, that is net upward pressure in y direction, is equal to 110 kN per meter square, because no moment is applied and your upper pressure is same in all the positions. Okay, so the formula will be similar: net upper pressure multiplied area of the critical section. So our net upper pressure for both the position for x and y will be equal to 110 only. So 110 plus 110 divided by 2 multiplied by 0.453. What is 0.453? So this will be your critical distance in y direction, multiplied by 2.5. Okay, so this how we have calculated for x. Similarly you have to calculate for the y. Okay, for the y direction. So this will be your y direction here, and this distance will mark the area. So this distance will be your critical distance. So this will be equal to 0.453. Okay, 0.453, you can just find out. This will be your critical distance. Okay, this whole portion. Okay, forward direction. So it is equal to 0.453 multiplied by 2.5. This will be your critical area. So here it is. Okay, and it will come as 125 kilonewton. Similarly VU ultimate will be 1.5 into 125, that will come as 187 kilonewton. So nominal shear for Y will be VU upon BD. VU will be equal to 187 to 1000 divided by 2500 into 432. So P will be 2500 here, that is the width of the footing in Y direction, multiply with your effective depth in Y direction. So it will come as 0.173. K will be taken as 1, as our total depth of the footing is same, that is greater than 300 mm. Percentage steel will become as, what percentage steel we are given in Y direction, that is 2261, multiply by 100 divided by 2500, that is width and the effective depth, so it will come as 0.209. And tau c depth will come by the same interpolation method from table 19, so it will come as 0.332, and our design shear strength will be multiplied by our K value, so it will become as 0.332 Newton per mm square, which is much more greater than our nominal shear strength. So this will be also safe in y direction. Okay, so if you don't need to find for the y direction. Okay, if you find for x direction where the varying moment is applied, so this will be in more in longer side, that in x direction. So once you find for the x direction, you don't need to find for the y direction, but how it is calculated I am shown here, you can get it. Okay, check for, so this will be check for two-way, that is punching shear, so it will also be called a punching shear check. Okay, punching shear check. So why it is called a punching shear? Because so this check will be applied, so your column will not be punched into the footing and fail. Okay, so here what you have to do, you have to consider the average depth in the place of effective depth. Okay, because it will be away at a distance of d by 2 from the face of your column, and here your distance will be different, and here it is taken from the all the footing edge surface, so it will be taken from here in this direction, this type. Okay, so d average will be equal to 438 mm, where we have already done in our first lecture. Sorry, this is d is equal to 438 and d average by 2 will be 219 mm, that is this. So our critical section is at a distance of d average by 2 from the face of the column. Okay, so we are considering this area because here our moment will be maximum. Okay, so that's why we are not considering here, because our ultimate net upper pressure is less than here, so we are considering here this value from this side. Okay, because here it is more than this side. Okay, as we have shown in diagram, so net upper pressure will be more here, so we are going to consider this area only. So px will be, that is net upper pressure at critical section in x direction, will be equal to 135 kilonewton per meter square. So by using the same method of interpolation, and we have to give the value, so it will come at a distance of 1.684 from this corner face of the footing. Okay, so how it is calculated, you have to first find the total distance, and after that you have to just minus this value, that is 430 minus d by 2 minus d by 2. Okay, or you can add 430 plus d by 2 plus d by 2 and just subtract it from your distance from here. Okay, so it will come as 1.684. So our upper pressure will become as 135 kilonewton per meter square at critical phase. So we will be equal to, so here 4 will be here, the equal to 135 plus 182 by 2, that is average of this, multiply by 0. Our your critical section, that is 0.668, this distance. Okay, this column face total distance 0.668 plus 0 total width of the footing, that is 2 meter, divided by 2. So this average area will come, multiply by 0.816. Okay, so it will come as 172.53 kilonewton per meter square, and VU ultimate will be multiplied by 1.5, so it is 258.8 kilonewton per meter square. Now tau v, so this formula will little bit different from one way shear, so it is equal to VU upon B naught T, and here your B naught will be this 668. Okay, you don't have to take the footing area because we are going to check for punching, so here we have to take the value from the column area only. Okay, so it is 668, that is the total shorter side of the column plus effective depth d average by 2 plus d average by 2. Okay, that will come as 668 multiply by 430, that is d average. Okay, it is average depth of the footing, so it will come as 0.885 Newton per mm square, and it is mentioned on page number 57 on IS code 456 2000. Now tau c dash will be equal to Ks into tau c. Okay, so this will be a design shear strength. Okay, so Ks into tau c, and it is mentioned in I score 456 page 58 and 59, and Ks value will be equal to 0.5 plus beta c, and beta c is equal to your ratio of your shorter side of footing to the longer side of the shorter side of your column to the longer side of the column, that is 230 by 430, and it will come as 0.53. so Ks will be equal to 0.5 plus 0.53, and it will come 0.064, but you don't have to consider the value more than 1. So if value will coming as more than 1, so you have to take the value of Ks as 1 only. Okay, so if value of Ks will come as less than 1, so you have to take that value, but if your value will come more than 1, so you have to take the value as 1 only. Okay, so Ks we are considering here as 1 only. Now our tau c dash will be equal to tau c into Ks. So tau c is equal to 0.25 multiplied by fck into Ks, that is 1. So 0.24 multiplied by fck is 25, so square root of 25, so it will come as 1.25 Newton per mm square, and which is greater than our tau v. ठीक है, nominal shear, so it is 0.885, so this will also be safe in punching shear. Okay, so here it is maximum at the critical section, so you don't have to find for y direction. Okay, so this will be a longer side, and here your maximum p ultimate pressure is coming, so this will be safe for two-way shear only. Okay, so now we have to check for the transfer load at the base of the footing. So this will be the formula for the uniaxial movement for the calculation of force at the base for uniaxial movement footing, equal to actual bearing pressure or pressure at the base of the column will be equal to P, that is the load of the service load of the footing on the footing, service axial load on the footing divided by area of the column, that is 550 into 10 to the power 3 divided by 430 by 230 plus moment in x direction. So either you in uniaxial moment, either your mx value will be provided, or your my will be provided, you have to mention that. Okay, so here our mx moment is given, so we have taken for mx only. So if it is given for my also, so you have to consider this value for my divided by my for column. Okay, sorry, zx zy for column, so it's section modulus for column. Okay, so in Excel sheet I have given for both the mx and my, so you have to directly fill the value only if moment is given for x direction, that is major moment, or if moment is given for y direction, that is minor moment, so you can directly calculate without any problem. Okay, so now it is equal to plus mx by zx for column multiplied by 1.5. Okay, so it will come as 550 into 10 to the 3 divided by 430 by 230 plus mx, that moment in x direction is 150 into 10 to the power 6 divided by zx, so it is b d square by 6. So what is b? So you have to take the value from column only, it is 230 multiplied by d, that is the your depth of the column. So d square it is 430 into 430 into 1.5. So why we have taken 1.5? Because we are taking the ultimate values. Okay, so our value will come as 40.09 Newton per mm square. So this will be the actual pressure that is coming at the base of the column. Now we have to check either it is our column base or footing top will be able to take the pressure or not. Okay, so capacity or pressure at the base of the column with which can be withstand will be equal to 0.45 multiply fck, so 0.45. so here you have to consider the grade that we have given for the column only. Okay, that's why we have taken the grade of the concrete for the column also at the starting for the column. Okay, that is M20. So here you have to take that value only. So it is 0.45 into FCK, that is 0.45, sorry, 5 into 20, it is coming as 9 Newton per mm square, which is less than your our calculated, that is actual pressure. Okay, it is less than this. So here you have to provide a double bar at this position. Okay, because our column is going to take the load up to 9 Newton per mm only. Okay, and here our actual load is coming as 40.09 at the base of the column. Okay, this will be our base of the column. So you have to provide a double bar here. Similarly, you can check for the footing top also. The position for the both the base of the column and top will be same, because but we have to check for both the values. So capacity of pressure at the top of the footing, which can withstand the pressure, will be equal to, this is the formula, 0.45 into FCK into A1 by A2, and A1 by A2 will be your area of the footing upon area of the column. Okay, or area of the cross section, whichever is greater you have to take that value, and it is generally be taken as 2 only. Okay, in most of the cases this value A1 by A2 is 2, but if you don't know how to find this A1 by A2, you can just check my previous lecture for square footing, you can get the answer. Okay, so it is equal to 0.45 into FCK multiplied by square root of A1 by A2, and it is 0.45 multiplied by 25. This will be the grade of your footing. Okay, multiply by 2, that is square root of A1 by A2 value will be 2. Okay, so our footing load will come as that footing can bear will come as 22.5 Newton, but it is also less than our actual pressure, that is 40.9. So you have to provide a double bar according to the this also. So you have to give the double bar here. Okay, so extra load, so you have to find the extra load that is coming at the base of the column. So it will be 40.9 minus 9 come as 31.09, and extra load due to pressure at the top of the footing will come as 40.09 minus 22.5 will come as 17.59, and here, so this will be your extra load. I have to find the extra force at the base of the column. So it will be 31.09 multiplied by your area of the column. So it will come as 30.374.43 kilonewton, and extra force at the top of footing will come as 17.59 multiplied by area of the column, and it is coming 1739, and you have to find the area of your dowel bar and take by taking the maximum of this value. Okay, so to take the maximum of this value, so extra dowel bar area will be equal to, so you are going to consider the 3074 force multiplied with 1000 divided by 0.75 into Fy. So this will be the formula. Okay, for the calculation of dowel bar, and it is given in high school 456 only. You can check from there also. So now we are considering the we have calculated the extra dowel bar area is equal to 9878, that is the 3074 multiplied by 1000 divided by 0.75 Fy. Okay, and dia of bar will be equal to, we are considering for the dowel bar is 25 mm. The number of bar will be calculated as 0.9874 divided by pi d square by 4, that is 3.15 into 25 into 25 by 4. So it will come as 20 number of bars. So you have to give the dowel bar at the base of the footing, sorry, at the base of the column and top of the footing, like this. Okay, this orange bar that sorry, this two that was showing here, and it will be bent like this. So this will be your dowel bar, and this black one will be lapped in column bar. Okay, So number of bar you have to provide as 20 number of dowel bar, okay, is footing here. Okay, now we have to also find the final weight of the footing that we have got. So it will be the area of the footing multiplied by the load that is coming into density of the, sorry, this will not be a load, this is the total depth of the footing. Okay, 1 minute, I just check, and it is the total depth of the footing. I am just checking whether it is, I have done anything wrong here. Okay, it was right here, no problem. And here it is safe. So this will be the area of the footing total into density of the concrete that we have taken. So it is 2 into 2.5 area multiplied by the total depth of the footing multiplied by density of concrete. So it will be equal to 62.5 kilonewton. So this will be the final weight of the footing, and at the starting we have considered a 12% of the load that is coming from column. So our 12% will be 12 by 100 into 550, so it will be equal to 66 kilonewton. So we have considered the larger value than the final weight that we have got here, so this will be safe. If this value will be less, so you have to again increase the initial percentage of footing. That's why I'm not taking the 10% of the self weight. Okay, that's why I'm considered the 12%, because I know that if we consider the 10% here, just check, I will show you here in Excel sheet only. See here, if I will just do the self weight of footing as 10%, so at the end, if you will see here, final weight of the footing, so if you show you increase the self weight of the footing, so again we have to increase the self weight of the footing. So that's why you had taken the percentage of footing as 12, self weight of the footing as 12%. Okay, so here this will be also saved, and we have completed our design of uniaxial eccentric footing for rectangular column. Okay, and this will be the bar position, how it will be laid, and this green portion will show you the first layer of bar, this orange one is the second layer of bar, and is the this blue one is your dowel bar that is coming, that is 20 number of bar, and it will bend like this. And we have also done the calculation for the development length, and we have already done separate video for the development calculation. You can check from there, I will provide the link at the end of the video. Okay, and we have already given in Excel sheet how you can calculate the development length according to your HOHT bar or meld bar. Okay, so I'll provide the link of the Excel sheet in the description only, you can download from there. So if you like this video, please subscribe to my channel. Thank you.